Hello and welcome. My name is Scott Sherman. I'm the engineering manager with Nexus Energy Technologies. I'd like to welcome you to the rebroadcast of the webinar that we did on April 29th, 2020 with ICoTA Canada. So just quickly, I would like to thank ICoTA's sponsors. We recognize the challenges of this quasi-normal and appreciate your continued support. So for those of you who are unfamiliar with Nexus, we are a manufacturer of pressure control equipment that specializes in coiled tubing pressure control equipment challenges. I have a list of questions that we captured from the live presentation of this that I will go through at the end. This paper was prepared for the Coiled Tubing and Well Intervention Conference in the Woodlands, Texas, but given the times, that conference was canceled. The paper is still published in One Petro and was written in conjunction with Trican Well Service, and I'd like to thank my co-authors, Sean Majko and Jeff Otto. So the advancements in coil tubing metallurgy in the past 10 years have been absolutely amazing. I mean, the standard of the art used to be 70 grade coil tubing, and now 140 grade is commercially available. And the big game changer has been quench and tempering coil. This has extended fatigue life. It's increased the hardness of the pipe, which in theory makes it less susceptible to damage in the wellbore. And given the additional strength of coil, it's less susceptible to operator damage such as overpull. So we wrote this paper because, you know, as coil tubing has evolved in the last 10 years, some of the accessories haven't evolved. They've remained largely unchanged. Coil connectors, for instance, are still the same coil connectors that we used to run with 70 grade coil. And these days, the coil connector will fail before the coil tubing will. BOPs now require more than double the hydraulic force to cut coil than they once did. And the reason it's more than double is because, yes, the shear strength has doubled. You know, the shear strength, as you know, is a function of yield strength. But the other thing that's changed is the wall thickness has increased significantly as well. You know, it's common to get 130, 140 grade coil in like 175, 204 wall. We've seen 256 wall. These are all things that, you know, 10 and 15 years ago weren't thought to be possible. This isn't the paper we wanted to write, but kind of given the time constraints of doing one of these papers, this is 3.5 months worth of work. And just to put things into perspective, you know, we submitted the abstract to SPE in August. We found out that the paper was accepted mid-September, and we had until the end of December to procure samples, apply the damage, ship them to Texas for bend fatigue testing, review the results, and write the manuscript. We do plan to follow up with this paper on shear forces and pressures required to cut various grades of coil tubing, including high-strength coil tubing in the future. So given that new strengths of coil tubing have higher yield strength, it follows that the hardness has also increased. We wondered if these new harder grades of coil were more susceptible to fatigue life degradation from slip marks and other mechanical damage than regular coil tubing that we've used in the past. So, you know, the authors went back and forth on kind of the best way to get this accomplished. You know, our thoughts were that if we went with kind of 188, 190 wall thickness, that should be pretty available. And we wanted to get samples in 95, 110, 125, 130, and 140 grade quench and tempered coil. We also wanted to get some samples of 100 grade conventional coil that we could use sort of as our standard to compare to. The plan was to hold the coil in a set of pipe slips in a BOP and pull 100,000 pounds of tension into the coil, remove the coil, and send it out for bend fatigue testing, and see if we could find find a trend or a difference between the conventional sample and the higher grade samples. We chose 5,000 psi, and we used that for all samples, and a 72-inch radius bend form. That was the plan. This is what we actually did. So procuring the samples from some of the mills was a little more difficult than we anticipated. So, in the previous slide, I noted that we are kind of targeting 188, 190 wall, and you'll note that not one of our samples is that wall thickness. So the 95 grade coil and one of the samples, a 130 grade, they are 204 wall. The 125 grade was 236 wall. The 110 was 175 wall. The other 130 grade was 175 wall, and the conventional was 175 wall. So you can see that we kind of were at the mercy of our suppliers as to what they were able to provide in terms of samples in the tight time frame that we had. But we went ahead with what we had. We continued with our plan of, pulling 100,000 pounds in. We measured the depth of the slip marks because, knowing that the wall thickness wasn't consistent from sample to sample, we tried to glean as much information from the samples as we could. And we still continued to do the bend fatigue testing at 5,000 psi on the 72-inch bend form radius. So this slide just shows some pictures. So the picture in the top left is a set of coil tubing slips from a BOP. Just kind of shows the serration pattern. The middle top picture, that shows the resulting slip mark damage after we applied the slips and pulled 100,000 pounds of tension into the coil. Top right photo is a photo of the bend fatigue machine that was used. So this is one of the Steve Tipton style bend fatigue machines. The bottom left is a picture of our single BOP with the pipe slips in it, and the pipe, and the bottom part is the ram that we used to pull tension into the pipe. And the bottom right photo is a picture of imprint using metrology putty of the slip damage being examined on an optical comparator, which is what we use to measure the mechanical damage to the slips. So this is the bend fatigue results for all the samples. So you can see that there's a fair amount of disparity here in the two samples that were tested for each of these, with the exception of the E samples on the far right. We'll kind of talk about how we tried to normalize the data in the next few slides. This is the raw data, and the thing that I'd like to draw your attention to here is the average hardness column, which is the third from the right. You'll note that what we found interesting here is that there's two grades of 130 pipe. There's the top one and the bottom one. And the hardness is considerably different between the two. So the top one, which is 130 grade, is 30.6 Rockwell C on average. And the bottom one, which is also 130 grade from a different mill, is 38.1 Rockwell C. So quite a difference in hardness between the two samples. So, here's some of our learnings from the results. I mean, we were a little disappointed with the inconsistency of the results initially, but we did find that every sample cracked at the root of a slip mark, and that's what we expected to see. The cycles to failure, there was quite a range from sample to sample, even within the same specimens. A direct comparison of the coil tubing grades was very difficult given the varying wall thicknesses. More test specimens for a given coil tubing grade may have allowed for the trends to become more apparent. But the bottom line, based on the results that we saw here, is that higher strength coil tubing doesn't imply higher hardness, which was quite a shock for us because, the mechanical engineer in me sort of is screaming at me going, wait a minute, there's a well-established correlation between yield strength and hardness, and based on these samples, we didn't see that. So, this slide here, we are comparing coil tubing hardness versus the slip mark depth. Again, trying to see if a trend existed. And this is pretty scattered data. It's difficult to say yes, if you have harder pipe, you're going to have less damage. And the reason I say that is if you look at the sample with Rockwell C of 24, it actually had a shallower defect depth than the coil tubing with the hardness of 38. So we didn't see the correlation there that we expected. So this slide talks about the cycle life reduction versus coil tubing hardness, because we thought there might have been a trend there. And again, it's pretty difficult to draw any conclusions from this data. The one thing that you'll see, reoccurring over the next few slides is that the cycle life reduction, let's face it, it's, on average between the two samples for each specimen, kind of between 20 and 45%. And I think that's kind of what to look for or what to expect. But there wasn't a great correlation between cycle life reduction and hardness. So then we looked at the cycle life reduction as a function of defect depth. And the defect depth, because the wall thicknesses weren't consistent, we did it as a percentage of wall thickness instead, thinking that might be a little bit more meaningful. And again, no great correlation there. But I mean, of course, it's still cycle life reduction on the vertical axis. So that 20 to 45% still continues to jump out. So in conclusion, the mechanical damage from the BOP slips, it does decrease fatigue life. We expected that. Based on the samples tested, the decrease was 1.6 to 56.6%, but sort of the average was sort of that 20 to 45%, as shown on the other slides. So I think I would use that as sort of a safe number. And just bear in mind that it's not just setting the slips on the pipe. That would have been less damaging than what we did. We set the slips and then we pulled 100,000 pounds of yield in. So we got a stress concentrator right where the slips are as well. The reduction in fatigue life is more dependent on the sample than the coil tubing grade hardness or defect depth. The results were a little more scattered than we would have liked, but the bottom line is that based on this study and the data that we collected, high grade coil tubing or high strength coil tubing is no more or less susceptible to fatigue life degradation than conventional coil tubing, and that's based on that sample of 100 grade conventional pipe. So recommendations, if we were to do this again, all coil tubing samples must have the same wall thickness. I think a data set of 2 probably wasn't big enough, but given the time constraints that we had, this is what we were able to procure. If we were to do this again, we'd look for, more like 10 samples of each coil tubing grade to get, hopefully we could start to see some trends emerge. And one thing that we didn't do and sort of regretted as we were writing the manuscript is that, when you do bend fatigue testing, you always orient the ERW, so the seam within the coil tubing, in a particular direction. And we didn't take care to do that when we did our slip testing. And perhaps had we done that, we might have seen a little bit more consistency in the data, because the slips would have been always oriented in the same direction when it was applied, or the slip marks would have been oriented the same on the samples when they were put in the bend fatigue machine. May or may not have had a difference. I kind of think it would have, but again, we don't have the data to back that up. So next steps, we're going to continue to add data points to the study over time. We're going to look at optimizing the slip geometry to minimize the effects of slip damage on coil tubing. We have an ongoing project on that right now. One thing that Nexus does is that if we have a customer or a prospective customer that has something unique that they want to run into a wellbore using coil tubing, or not, we're always happy to sort of add to our shear database where we, we'll try and cut anything within reason, of course. We've done lots of testing on things like co-rod and flat pack, concentric coil, all those sorts of things. So if you have something that you want tested, send it to us. We're happy to test it. We work with all of the coil tubing manufacturers to ensure that we're able to cut all of their new high strength grades of coil tubing or heavier wall coil tubing that they bring to market. And we'll continue to do that. And, as things progress, we're going to continue to evolve coil tubing, BOPs, and pressure control equipment and make sure that it's future-proofed for all grades of coil tubing. So just by way of acknowledgements, I'd like to thank Gary and Fernando of Global Tubing. They took care of running Trican's bend fatigue machine and compiled the bend fatigue data for us. Ian and Abner were instrumental in assisting with the testing and subsequent measuring of the defect depths. So yeah, they were very helpful. And again, I'd like to thank the manufacturers, Global, Tenaris, and Quality, for providing samples for this study. And I'd like to thank Trican and Nexus for allowing us to present these results. So we did have some questions submitted when we did this live. So I'm just going to go through those questions as a recap. So the first question was, 1.6 to 56% is a large range, and what derating would we recommend? And kind of, as I pointed out before, don't forget that it's not just setting slips. We also put an overpull on the pipe of 100,000 pounds. But kind of based on that, I think that local derating of 20 to 45% would be reasonable and safe. I guess as the saying goes, your mileage may vary. Question 2, did we do any validation of the actual yield strength of the pipe? And I think this question was directed at the fact that the hardness was different on that 1/130 grade sample from the other. And there may have been some doubt as to the actual yield strength of that sample. And no, we did not do any tensile testing or validation of the actual yield strength, or to determine the actual yield strength. That was outside the scope of the paper. Next question was, did we have any fatigue failures across the seam weld? And that wasn't something that we looked at specifically. So I can't say yes or no, but it's not something we confirmed or looked for specifically. Question 4 was, did we request samples from outside North America? So there are some Asian mills that are making coil tubing, in the last 5 or so years. But to my knowledge, the author's knowledge, we did not think that they are making quench and tempered coil tubing, and so this study was limited to quench and tempered coil tubing plus the sample of conventional coil that we used as a standard. So question 5 was, does the timing of the slip contact change anything? And that gets back to my point in my recommendations, where we would ensure that we oriented the slip contact so it was consistent, so it was oriented in the same direction the bend fatigue machine. So that's not something we tested, but something, if we were to repeat this testing, we would definitely do in the future. Somebody else asked if there were any H2S effects, and that was not within the scope of the paper. So we did no H2S testing, and aren't in a position to comment on what would happen or what would have happened differently if the pipe were exposed to hydrogen sulfide, before we did this. And I guess it's worth mentioning that we used all new coil tubing samples for this. No used samples were used. So the next question was, were all samples tested at the same pressure? And yes, we tested every sample at 5,000 PSI. Follow-up question was, did we check for ballooning and ovality periodically during the testing? So that question was submitted by a previous colleague of mine, and he and I used to do bend fatigue testing. And what we would do is we would, depending on the test, we would periodically, maybe every 10 to 25, 50 samples, depending on what we were doing. We would stop the bend fatigue machine and measure the for ballooning and ovality to see if we needed to continue with the test. And the significance of that was many of these quench and tempered coil tubing grades, they will run for hundreds and hundreds of cycles. But what we found in the bend fatigue machine, which isn't fully representative of the field, was that the ballooning would become so extreme after, maybe a couple hundred samples, or sorry, not samples, a couple hundred cycles, that, it wouldn't fit through the brass on a BOP. So we kind of end the test at that point in some cases, depending on what we were looking for. And we did not do that as part of this test. Next question was, does slip variation play a role in this? So, the way that we look at BOP slips is that, they're for use in an emergency. And we are looking at making the slips a little friendlier to the coil, but, the bottom line is we don't want to put any of our customers' employees at risk, or, the economics of the well at risk, by developing BOP slips that are really friendly to the coil, but they won't bite the coil in all circumstances. And, we need to bear in mind that coil tubing, in service can be, 20 thousandths of an inch undersized. It's never round. It's always slightly ovaled. We don't know what that orientation is going to be like. So, we've got slips that will bite the coil regardless of its condition. Next question was, if all samples saw the same bend fatigue test pressure, regardless of wall thickness, the tubes would have seen a different stress load. Did you consider this? And, that's a really interesting comment. That's not something that we considered, but a great point. And that's one of the difficulties of getting the samples with varying wall thickness. One could even take that a step further and saying, because the wall thickness varied, the tensile stress that we applied to the samples also varied when we put the 100,000 pounds of pull into them. So we could have considered that as well, but didn't. I mean, given the time constraints of writing this paper, we kind of, well, these are the samples we got. Well, okay, let's stick with the plan. But in retrospect, that's a really great comment. Next question was, has this testing been done before? And so, to our knowledge, Graham Wild of BJ Services did a study like this 20 years ago, something like that. But we looked high and low, and we've been unable to find the paper that was written that went with that. And it may have been an internal paper at BJ. Yeah, we couldn't find the reference. We looked for that and would like to have cited that as a reference or used that reference material. But again, that was not done with quench and tempered coil tubing because that work predated the development of quench and tempered coil. Next question was, the additional force required to cut quench and tempered coil tubing, what about cutting under pressure? So, in our lab, we don't normally cut pipe under pressure. It's something we could do, but generally do not. But I mean, let's face it, a 15,000 PSI BOP, it's designed to cut any type of coil tubing at 15,000 PSI. So, depending on the design of your actuators, there could be additional pressure effects from pressure in the wellbore, but we've got that already considered in the design of the BOPs. And that concludes the presentation and the questions. So I'd like to thank everybody for tuning into this and watching. And if you have any subsequent questions, please reach out to Nexus, and we will do what we can to get your questions answered. So once again, thank you very much.